Hello, my name is Andres Starkov from the University of Washington, and together with my colleagues Linda Bushnell and Rada Puvender, I'm going to talk to you about an algorithm we came up with that we call fast inverse instance-based learning. Let me start by telling you where this algorithm actually might be useful. Our main intention was to devise an algorithm that would allow you to understand the intentions of other people, or describe the way you might understand the intentions of other people from their actions. This is a scenario that is typically referred to as theory of mind or metacognition. And it's particularly important in situations where there is limited communication. You can imagine that this situation arises, for instance, in cooperative scenarios where, for instance, two people are trying to collaborate to solve the same problem, but they don't have a chance to exchange communication, like these two scuba divers, or in adversarial scenarios, like when you're playing against one or more opponents, and in this case, the communication is poor because it's intentionally withheld, and you're trying to understand what other players are trying to achieve. Now, of course, this is not a new problem, and in fact, is a problem that has been studied a lot in the field of reinforcement learning. And there is a state-of-the-art family of algorithms called inverse reinforcement learning that purportedly does exactly that. It takes a series of actions and tries to reconstruct what are the rewards that another agent associates with these particular actions and states in the environment. Fact is, the current state of the art is also notoriously limited. Inverse reinforcement learning doesn't work that well, which is something I try to capture with this kind of like picture. It would be possible, it would be great to use an optimal algorithm like RL, but it doesn't simply work as well as we want it to. So in this talk, I'm going to try to convince you that the algorithm we came up with is actually better and more flexible than inverse reinforcement learning. And most importantly, it doesn't really require the underlying model of the agent to be RL. And in fact, it uses a simpler model that is also cognitively plausible, a theory known as instance-based learning. Now, instance-based learning is a very kind of like dominant paradigm in the cognitive sciences, although it's not as well understood outside of the domain of cognitive science or decision making. It was originally proposed by Christian Lebert and Coti Gonzalez in 2003, and it's based on the idea that smart agents, in particular humans, make decisions based on memories of past experiences. We call this as an episodic memories instances, and they are typically characterized as triplets of three components: a general state in which the action applies, an action that was taken in that particular state, and a utility or a way to capture the outcome of a particular action, a particular state, as a number. We can consider this utility, and in this case, I will use this simplifying assumption, as just the evaluation of the successor state. So if taking an action in a particular state produces a result that is good, a new state that is better, it has a higher utility. Now let's actually apply this to the case that we're all familiar with, the case of playing a board game like Settlers of Catan. Any given player, imagine this player here, has a previous history of interaction with the game, and this history is captured by a database of stored instances of what happened when different actions are applied to different states, and what are the results of these games. So at any moment in time, our player might be facing a particular new game state and might be scanning its own episodic database for relevant situations, instances, and memories that are similar enough to the current state. At that point in time, it will just consider all the possible actions, examine their respective utilities, and make a decision, likely based on the best action that led the best utility, on the next action to take. Once this action is taken, our agent can evaluate the results of this action. In this particular case, it actually won the game, and form a new episodic trace that ties together the state, the action, and the new utility. And this way, learning perpetuates itself. Now, to get to our algorithm, we need to be a little bit more precise on the tenets of IBL. And to simplify this, I'm going to give you IBL described as three fundamental principles. The first one is that memories are not static, but they decay over time. So memories that are experienced, instances that have been experienced a long time ago, are less relevant to the current situation than ones that are immediately recent. This is captured by saying that each particular instance has a particular probability P at any time T of being selected for evaluation. And this probability goes down over time as a function of time. We can also consider the entire matching set, so we can also specifically define the probability of an instance to be selected as the activation, the amount of time that has passed elevated by this exponent, divided by the sum of all the competing activations or the competing instances. Now, this is a good way to capture like our instances in the past are less relevant to now that instances are recent. But of course, there is another problem, and the problem is that different instances, even for the same action, might have associated different utility values. In this case, the solution is a principle called blending. And the idea of blending is that we kind of like average the best possible utility that represents the value of a particular action as the utility that minimizes the difference between the blended value and the distribution of all the other experience utilities. You can imagine that this gives you a prototypical value for a particular action that takes into account our, previous experiences are faded to time, but also what is the distribution of values that you have. In the case of simple numerical values, you can also reduce this equation significantly and just say that the blended utility of an action is just the sum of the associated probabilities for each particular instance in which the action appears and the corresponding value. Finally, the last principle is that agents in IBL select an action based on a softmax system. So given a particular state, there might be different actions, but now we have a way to capture the blended utility of each action, and we can select noisily between these actions in a way that actually gives action that have higher utility a greater chance to be selected. Okay, now that I've aligned all these three tenets, we can look at how we can use this principle and invert it for metacognition and theory of mind. In essence, what we're trying to do is to create an inverse IBL that will give us the utilities and the goals of an agent given its history of actions. And we need to perform this inversion because all you can observe on another agent is typically the series of state actions. So you can see the overall behavior, but you cannot see the internal motivations. And in particular, we cannot observe the internal utilities that an agent has stored about the result of their actions. However, the utilities are exactly what we need to understand to imagine or make an inference about what state the agent is trying to achieve. So remember here, because we're going to refer to evaluation in slightly different context. So there is two different meanings in terms of evaluation. One is the retrospective utility of past action and states, which is known, we specified by the theory. And the other one is the evaluation of the outcome state, the successor state S, which is unknown, and is what we want to discover. And in order to perform these two steps, we need to articulate this algorithm in this following way. The first step is just the step of inferring utilities. So this is actually non-trivial because, again, as I mentioned before, we only have a series of states and actions, and we need to have a way to infer what is the experience that an agent has when he observes the results of a particular action. The second step is to go from these reconstructed utilities to what the agent wants to achieve, the estimated evaluation function of the agent, which of course is associated and reconstructible because if we know the utility of a particular action, we know that this probably came from evaluating the successor state. So if we know the utilities for a particular action, we can also recover what is the state that an agent values the most. So let's break down this algorithm into the two steps precisely. Let's go back to the first step in particular. How do we infer utilities? Well, in order to do this, we need to go back to the IBL's decision policy. You might remember that IBL makes decisions by using the softmax action policy, where basically all the actions are compared on the basis of the blended utility. Now, we're going to make an assumption here. We're going to make an assumption that this quantity is constant, and we're going to call it K. And if we consider this, you can see that the utility of a particular action in a particular state can be expressed in terms of the noise temperature of an agent, multiplied by the log of the probability of an action, which is just empirically estimated by observing how many times an agent has taken that action in the past in the particular state, plus a constant. In fact, we can even find a specific approximation for the constant if we assume that on average, the mean utility of a particular action is a constant. In this case, I'm going to assume 0. Under these circumstances, you can express this constant as 1 over the number of actions multiplied by the sum of the log values of the probabilities of seeing any other action in this case. This means that now we have an empirical estimate from the observed actions of what is the retrospective utilities that the agent has estimated for each particular action. And they come from like the noise aspect, the frequency at which actions were chosen, and the frequency at which all the other actions were chosen in a similar state. Now, if we do this, we can now make a step that let us allow to discover the individual utilities for all the actions that we have observed. You can notice immediately that, of course, we have an estimate, which I indicated with the U with a circumflex accent, that is not actually the predefined theory estimate of it. But there is a relationship, and in theory, the two should be equal. So we can just select a vector of utilities that minimize the difference between the mandated quantity defined by the theory and our estimates. And a common way to do this is to use something like ridge regression, something that gives you a robust estimate of this particular vector of utilities. Once we have this, we can move on to the next step and recover the goal. And remember that the system will give us an evaluation function for every state that we observe, and the goal that an agent wants to achieve is simply the state that has the highest evaluation. And now we can make inferences about an agent state. To test this algorithm, we design an experiment. It's a dynamic control task that is a famous task used in cognitive psychology. It was known as Sugar Factory for over 4 decades. And it's a simple dynamic control task because what the agent has to do in this case is simply control the output of a noisy imaginary factory where the output of sugar O is related to a number of workers that are located at any time t by this dynamic equation. Now, this is actually a very unstable system, and both humans and artificial agents struggle to keep the production to a particular type output state. So this is actually the perfect test for our case. So can we discover, observing a limited set of actions, what is the state that an agent wants to maintain, even if the state and the output that we observe are extremely noisy? So to test this, we created over 1,200 artificial IBL agents, and they were given the task of maintaining a random goal. So each agent was giving a goal between 1 and 12. We also provided temperature. It didn't really made much of a difference, and we gave each agent the opportunity to interact with the system for 500 iterations. And this is a sanity check to show you simply that, in fact, the agents did improve over time and did learn to control the system despite the noise intrinsic in the system. This is the mean difference between the observed and target state, and you see it goes down and reaches asymptote at a certain point. But can we recover what is the observed intended state an agent wants to go? Well, we applied Feeble to the area in gray, to the last 250 iterations. And yes, you can see that in general, Feeble is pretty good at recovering the general distribution of goals that an agent had. In particular, it has a fairly good recovery of 33%. And overall, even if it doesn't recover exactly the perfect goal, it doesn't fall too far from the intended goal. So for instance, in this case, like data in this point represent all the cases in which the goal of the agent was 7, but Feeble interpreted as a 6, which is still a very good thing. In fact, in general, if we observe the ranking of the agent goal listed by the distance from the target case, you can see that in most cases, Feeble recovers actually the perfect goal, and the second best is only 1 step away. The third best is 1 step away, and so on. So this is good, but it's only part of the story, right? So can we actually recover the entire agent preferences? So not only how much, what is the actual goal state, but how much the agent likes other states as well. And we can do that. So this is actually a case in which I can show you the true evaluation function that was given to our agent. So this is an agent that was given the goal of maintaining production of 4, and this tells you what is the outcome from the agent when the agent reaches the state 4, but also the outcome when he reaches other states like 2 and 5, or in this case 0 and 10. And this is just the function, the objective function that was given. We can, of course, recover this function, and you can see here an example in which that particular function was discovered as the function associated, the utility associated with each state in Feeble. And in this case, you can see that it's pretty similar, and it has a correlation of 0.85 with the actual evaluation function. In fact, we can do that with every single goal that the agents have experienced, and on average, FIBO recovers evaluation functions that have a correlation of 0.72 with the true functions that the agent had. And this is true in the case of agents that are, of course, themselves instance-based learning agents. But what if FIBO is used against RL agents? So we redid the simulations, and in this case, we created 1,200 RL agents instead of IBL agents. You can see the characteristics smooth learning curve RL agents. They still learn, but they learn differently, and they perform the task in a slightly different way. Well, as you can see, FIBO is insensitive to what is the underlying model of the agent. We can just assume that the agent is some sort of instance-based learning system, even if the underlying mechanics are actually RL and not IBL. And FIBO does a fairly good job. In fact, it's undistinguishable in terms of performance in recovery, both in absolute goal recovery and in reconstructing the underlying evaluation function of the agents. So to summarize, presenting an algorithm is a simple way to recover goals and preferences from observable behaviors. It is based on a simple but plausible model-driven condition, and it works with minimal assumptions, even if the underlying observed behavior doesn't come from an instance-based learning model, but from other type of agents like RL agents.